What my goal is now is to talk about laboratory experiments. And where I'll start is looking at the dry melt-free case, because that's where the biggest data set is. And I hope to make the point that we're understanding this better and better, and models like what Neil just presented are doing a pretty good job at representing that evolution of the crystallographic orientations. And then I'll introduce the case where there's a melt in the system. And this is a problem we've had data on for, I guess, 13, 14 years at this point. And it's still a bit confusing. And because of that, where I'll end up is necessarily more qualitative. So I'll present the observations, and we can think about how to interpret that and how to move forward. I really hope this ends up being motivation for bringing a more mathematical framework to this. Okay. So here's the basic point. So on the left side, this is the grain scale microstructure. Black lines are grain boundaries. Now, the color scale is related to orientation. I don't want to worry about that too much here. And this is in a rock deformed with below the solidus. Okay? And this is the sort of crystallographic alignment you get out. These are similar plots to what Neil just showed. In this case, there's one point for each grain. Right? So this point right here means that there's a grain in this microstructure, and its 1, 0, 0 axis is pointing in this sort of orientation. These are in the reference frame of the map. Okay? And so you can see a large concentration here, so most of the 1, 0, 0 axes are horizontal in this case. You can contour this, and it's like a probability distribution function, or as Neil is calling it, an orientation distribution function. And on the right is the case, this is from Ben Holtzman's work, where now there's a melt present, and it's segregating into these melt-ridge bands, so on a length scale larger than the grain size. And the key observation here is, on this side, 1, 0, 0 axes are in the plane of the screen, and in the case with the melt segregation, they're at about 90 degrees to that, the maximum in this distribution. Okay, so it's subtle, and you may think it doesn't matter too much, but it is a key indicator that there's something very, very different happening at the grain scale. Okay, so Ben Holtzman and Mike Kindle looked at this in some detail in a relatively recent G-cubed paper, and here's part of the problem is ambiguity. So we don't know the flow field in Earth's interior. We can make some predictions, and we'd like to be able to measure it. So let's assume we can have three different shear planes and shear directions, and roughly the melt segregation, these melt-ridge bands, will be subparallel to that shear plane. And that's reasonably consistent, but because we don't know the shear plane, we can have a bunch of different orientations. Then on top of that, we can think about this preferred orientation for the 1, 0, 0 axes. And if, it seems like there are two options. One, they could be parallel to the shearing direction, and in the other case, they can be perpendicular to that. And because of that, when we try and think about the anisotropic properties of this rock and how that affects the measured anisotropy and elastic wave propagation, we can't pick which of these scenarios is true. Okay, and yeah, so they did some exploratory calculations. So one thing they did was to take these melt-rich layers and make a suggestion about how the melt affects the elastic properties. And now you have a layered media where you have melt poor, melt rich, melt poor, melt rich. And these the Backus average, which is something that Jan talked about on Wednesday. And they can use that to calculate the aggregate elasticity. Superimposed on that, they also took into account a potential distribution of crystallographic orientations, which is going to impose its own anisotropic signature. And so we have these two cases, and they're plotted up here, and these plots, again, are these sort of stereographic projections, but instead of orientations, what's plotted on the left is the wave speed for, in this case, a compressional wave moving in in a particular direction. So right in the center of this plot, that'd be the p wave speed if you're moving, propagating normal to the page. Okay? In the middle set of plots, we're looking at the difference between the two shear wave velocities, because if you have a shear wave that propagates through an anisotropic medium, it necessarily splits into two polarization directions, and one wave is faster than the other, and this is the difference in those speeds. And on the right plot, this is showing the speed of the faster of those two S waves, and the black sticks on top of that show the preferred polarization direction of that wave. Okay, so the melt banding, that layered structure, imparts, this primary effect is these plots are mostly blue across their center. Okay. Oh, I should point out, sorry, these are plotted in the reference frame of this face on the side here. Okay. But superimposed on top of that, the crystallographic effect we see in the top one, we have faster p wave speeds normal to the plane, so along this green arrow. But in the right-hand case, or the bottom case in terms of the plots, that the fastest propagation direction is 90 degrees to that. Okay, and that's detectable. Right? So Neil mentioned azimuthal anisotropy. We're talking about a wave traveling parallel to the surface of the Earth, and its speed depending on the direction in which it's traveling. And you're going to sense these sorts of differences. Okay, and so it's a very big difference when it comes time to interpret that signal in terms of the kinematics. Okay, so as I say here, I'm going to focus on this crystallographic control rather than the effect of the melt phase in modifying the elastic properties. And as I just mentioned, there are applications to our interpretations of seismic data sets. But I've already alluded to this, a really useful aspect of this is thinking about what the underlying physical processes are at the grain scale. What are the differences in the deformation mechanism between these two types of samples? And again, we're going to end up, being pretty qualitative here, with some rough cartoons at the end to try and think about how to interpret these observations. Okay, so some of the key experiments that were done on olivine aggregates are shown here, a Nature paper out of Shun Kurato's lab in the mid-90s, and one at a ETH in Science. And in the top one, we're deforming an aggregate of olivine grains in this direct shear geometry. David mentioned this on Monday, but we have angled blocks that are forced to shear the sample. And you're limited a little bit in the amount of strain, and the deformation is actually somewhat complex. So it's nice to see that something similar was reproduced in this bottom set of experiments, which were done in torsion. And again, the key observation is that 100 aligns roughly with the shearing direction. Right? And this was assumed for a long time. Okay? Going back to the mid-60s, it was proposed that you could use this as a kinematic indicator. You map the fast propagation direction in the Earth, and you get out the kinematics. And this was nice confirmation that was possible. Okay, so now what I'll do is show you how we've increased the size of this data set and looking at more complex kinematics and seeing how well it agrees with some modeling. And I'll just step through the experiments. We've seen some aspects of this already, but I thought it would be fun to show some pictures. So we'll start with San Carlos olivine. Each of these is one crystal roughly. And we'll grind that into a fine powder. And we take that powder and then put it into a metal canister. And this is paired up with some ceramic pistons, and that's all inserted into a metal jacket. And that whole assembly is then inserted into this big white box. This is a Patterson apparatus at the University of Minnesota in Dave Kolsted's lab. There are two there. There are about 15 in the world. And we'll move around to the back side. So here is looking inside the box. This is where the pressure vessel is. And we'll look down on top of it. And so there's a bore out of the center. You insert the assembly into that cavity. You can seal it, pump it full of argon gas. That provides a confining pressure. You can internally heat it. There's a furnace inside of this and other instrumentation. And so we tend to operate about 1200, 1250 degrees C. There's a decimal point right there. Promise. And confining pressures of about 300 megapascals. And so at this point, that powder sinters into a dense aggregate, right? It densifies. And we've synthesized a rock out of powders that come from a natural source. At that point, you can apply some differential stress to your sample. And the typical thing would be to end load it, and you deform it in compression. In this particular case, we put a torque on the assembly, and we deform it in torsion. And David already showed some pictures like this, but just to point out again, you form a crease in the edge of the jacket upon pressurization that was initially vertical, and you see it's deflected on the part of the jacket where the sample is. And so this is taken to a shear strain of 5 or so. Okay. And so for working on olivine, we designed a sample geometry like this, where we're actually working on thin-walled cylinders of olivine. And the benefit of this is that it simplifies the mechanics of the test. And so we have this ring that we're twisting, so it's effectively an infinite shear zone. And you'll probably notice that this says FO50, and so I should point out that a lot of what I'll show comes from samples where we've doped them with additional iron. So we've made a very iron-rich olivine. And the benefits of that is that, I mean, the first order benefit is that it speeds up the kinetics. And so you can get a lot more done in the short time that you can operate the instrument. So we want to go to really large deformations. We like to be able to get to really high strain rates. Okay. So here's how these tests work. You start with something that's pretty coarse-grained to begin with, a uniform distribution of orientations, and you start twisting it at a constant rate. So we could think of that as like a constant strain rate. And you can see the stress that's necessary to maintain that rate. So there's a peak as you initially load it, and that dies off. It weakens and approaches some approximate steady state. And that weakening is associated with a refinement of the microstructure. Okay, you go from something that's really coarse-grained to something really fine-grained. You remember from Tuesday and some on Monday, we talked a lot about grain growth. But in this case, the grain size is actually being reduced. And we can get into the details of why that is if necessary. And we'll see that the orientation distribution also dramatically strengthens. You form this very strong crystallographic texture. And at that point, we'll start perturbing the strain rate, and you see corresponding perturbations in the stress. And that lets you map out the rheological behavior. Okay, so here are some of the measurements where we're plotting the strain rate as a function of stress on a log-log scale. And so you see what looks like a power law, and that lets you write a scaling relationship between the strain rate and the applied stress with some high exponent. You do the same thing for strain rate as a function of grain size, and again, you can roughly think of this as a power law with an exponent somewhere close to 1. Now, these are incredibly powerful measurements for us because it lets us relate it to simple micromechanical models to say, what is the dominant mechanism? And this is in reasonable agreement with a sort of mechanism where the rate is limited by the motion of dislocations inside the lattice. Okay? So much of what we talked about earlier in the week, the rate limiting step is diffusion of material and something like diffusion creep. But in this case, it's the processes happening in these dislocations. Now, the grain size dependence suggests that the number of grain boundaries in your microstructure is important. And the typical interpretation of this is that the grain boundaries are actually relatively inviscid, and that allows you to have stress concentrations at these triple junctions, and that controls how many places you can nucleate these sorts of dislocations. And so the more triple junctions, the more dislocations, et cetera. Okay. We tend to refer to this as dislocation accommodated grain boundary sliding to draw contrast with diffusion accommodated grain boundary sliding, which is what a lot of people associate with diffusion creep.
Is N 4 in this?
N is 4 in this, yep. There's a decimal point there too.
For the higher iron content sample.
Exactly, yeah. For some reason, the higher iron content samples are pretty consistently 4, as opposed to 3.5 for FO90. Okay, but same grain size exponent for both of them. Okay, so then we can be really bold and make an extrapolation to the Earth using this scaling relationship. I didn't show the dependence on temperature as well. Yeah, Rich?
The stress and strain rate you can vary during the course of the experiment, but the strain rate, I guess you only diagnose
Sorry.
afterwards. The grain size you only diagnose afterwards.
Correct, yeah.
So, is that just a bunch of experiments? No, the next plot.
Yes,
There's
yes.
just a
Each one
bunch
of
of
these is a different experiment. And the point is it's the reason to take it to really high strain is because the microstructure reaches this approximate steady state. The grain size has stopped evolving at this point. It's one of the big difficulties in this. You take something coarse-grained and you deform it just a little bit, you get a strain rate, but at the same time, there's a little bit of grain size reduction. And that potentially plays a role in the mechanical properties that you measure. So what we'll do is go out to go to really large strain at a particular stress. That locks in a particular grain size, and we get a set of data. We do the same thing then at a different stress, and the grain size ends up being different because there's a stress control on the grain size. Okay. All right. So here's this bold extrapolation. Again, this is just dry olivine for the upper mantle, so the top 400 kilometers. And I've colored this line according to what the dominant mechanism is. And so this blue part is is the mouthful of dislocation accommodated grain boundary sliding. And the point is that tends to be dominant over much of this region. Now, and Neil pointed out dislocation creep as a key mechanism in forming this crystallographic alignment. And I'll note that there's not a huge difference in my mind between these mechanisms aside from the grain size effect. Okay?
Lars,
Yep.
I probably should know that, but so which stress exponent did you use for this extrapolation then, for the grain boundary sliding?
I use the San Carlos olivine flow laws for this extrapolation because we have sets for both. We have it for FO90 and for FO50, right? But because I'm going to be talking about a lot of the high strain deformation, I showed the FO50 data set here. Is that all right? Yeah. So this is for FO90. Okay. I'll point out that if we take what we know about melt-bearing deformation from similar experiments, including flow law, I mean, there's a flow law for diffusion creep built into this. Right? So if I do the same thing for a melt-bearing aggregate, including a flow law for diffusion creep, we see basically the same pattern. So the current prediction in this sort of test is that these mechanisms are dominant, even in the melt-bearing case. Okay. All right. So let's look at the orientation distributions. So again, deformed in torsion. This is all yellow and green, mostly, which tells you about the texturing. And here are 5 different samples, and you see they all end up at about the same place. These are all after a shear strain of roughly 10. Okay. So we can change the geometry a bit and change the kinematics. And in this case, we've put a sample in extension. And same color scale, you notice everything goes purple and blue. And you can see that over here, our 100 axes are dominantly vertical. Okay, so they really respond significantly to the kinematics. All right. These are taken to strains of about what? Something like that, so much lower strain. Okay. The other beautiful thing about the torsion experiments is if you do use a solid cylinder, you can map from the very center all the way out to the edge. And the total strain is a linear function of the radius. And that means here I'm in the center, and as I move out towards the edge, I'm also progressing forward in strain. Okay? And so in this particular case, we first deformed the sample in extension, and then we subsequently twisted it. So in the center, we see the alignment associated with the extension with 100 vertical, and then as we progressively move through the sample, we see how increasing amounts of deformation realign the dominant crystal orientation. And we can animate this because it's good for talks, and also to make the point that it's a really rich data set. And the key feature you see in this is the average orientation sort of gently rotates. Okay? Yeah, and it takes a shear strain of 5 or so for that to happen. 3, 5, whatever. Okay. We can get even more into the details and look at the distributions, these individual distributions. So, I mean, these are a bunch of individual axes, so these are all vectors, and we can look at a matrix of the direction cosine, so this gets called the orientation tensor, and its eigenvalues give you a sense for the shape of this distribution. So here, plotting ratios of those eigenvalues. If we're more to the left on this plot, we tend to have points that are clustered, so a strong alignment. And if we're more to the right on this plot, then most of these directions all fall in a plane. So they're girdled. And you see something very different for each of the crystallographic axes, right? 1, 0, 0 becomes very, very clustered. These other ones sort of become more girdled and then less girdled, and there's a lot of subtlety. Okay. And then, you know, what we've been recently doing is taking this and trying to compare it to existing models similar to what Neil just showed, although we haven't compared it to that particular parameterization. We haven't compared it to the second order self-consistent model. In this case, VPSC is close to that, although it uses a different linearization scheme. And so these are data from one of these tests where we first put it in extension and then deform it in torsion, which is a complicated path. And so it's nice to see this systematic evolution, and the models are doing a pretty good job of capturing this, right? So I should point out that this plot is looking at this angle here between effectively the average a-axis 1, 0, 0 orientation and the shear direction. Okay? But they're not, you know, the models aren't predicting something with concentrations over there. Okay. So let's talk a little bit about the elasticity. And after a week that was heavy in sophisticated homogenization techniques, I mean, we're relatively crude about this. But we can still look for systematic patterns. And so, I mean, we start with linear elasticity, Hooke's law, and here's that stiffness tensor in Voigt notation, and it has all these zeros in it because olevine's orthorhombic, so it has this pattern that is orthorhombic symmetry, but all of these values are different, and we can measure this from a different set of tests for one crystal. Okay, but remember, we have a distribution of crystal orientations. So for each grain, you have to rotate that tensor into, you know, a geographic reference frame, and only then can you do some sort of homogenization. So you could take a simple volume average, so your Voigt average, or harmonic mean, so Royce, or if you really want to forget about the physics, you can take the average of those two, which ends up reasonably approximating some of the laboratory experiments. Okay, but at that point you now have a tensor for the whole aggregate, and to compare to something that seismologists might use, you can define this vector G that defines the orientation of the azimuthal anisotropies. So what's the fastest direction in the horizontal plane? Or what often gets used is the radial anisotropy. So this is saying we have a horizontally polarized S wave versus a vertically polarized S wave, and what is their relative speeds? That all comes from that average tensor that you calculate. Okay, so here are plots of what these look like for our samples. So we see that in the case of azimuthal anisotropy, these values go to 0. So this is telling us the orientation, so the fastest direction aligns with the shear direction. That's what 0 means. Okay, so that's good. It means we can use the fast seismic direction as an indicator of kinematics. And then here we see the magnitude of the radial anisotropy increase progressively, very systematic way, and appear to sort of saturate at some point. Okay, and again, these can be reproduced reasonably well with models like what Neil was talking about. Okay, so now let's go on to the more complicated case. Let's put some melt in there. And so again, as I started off saying, you know, we can see this big difference now. We've seen a lot of these plots now with 1, 0, 0 in the plane, and now it's pointing out at us. And what is going on? Okay, but let's start with a slightly simpler case. We can start in the case where there hasn't been a significant, or there hasn't been segregation of the melt phase at a length scale longer than the grain scale. So we don't get these melt wedge bands, but we do get alignment of the melt pockets. There's a shear top to the right. And in that case, what you see is the formation of these weak girdles of 1, 0, 0 and 0, 0, 1. Okay? And it's only when you have the segregation into these melt-rich bands in which you start to get these point maxima normal to the page here. Another weird feature is that, here, let me just go back. So in this case, the 0, 1, 0 axes form a strong point maxima that's vertical. And in this case, it's tilted back by about 20 degrees. And that is very consistent throughout all these experiments. All right, so what I didn't say at the beginning that I absolutely should have was that, I mean, this is work done with a lot of different collaborators, and the bulk of what I'm going to show right now was done, is from experiments done by Chichow, who is a graduate student, Dave Kolstad's lab, is now a postdoc at the University of Pennsylvania, working on ice, in fact. Okay, so here we're looking at mixtures of sand colorless olivine plus Marlborough, sand colorless olivine plus an alkali basalt, and the difference between the two melt compositions, it doesn't seem to be significant in terms of the crystallographic alignment, and we're generally working at melt fractions around 5%. Okay, and we're mapping the microstructure in detail. A quick word about how we're doing this, because I haven't said anything yet, is we're mapping this with a technique called electron backscatter diffraction. And Leila presented her grain size measurement techniques using this. I'll just say a little bit more about it. What we do is we lay down an electron beam on the sample, and that interacts with the sample, and some of the electrons scatter back out. And when they scatter back out, they diffract, and you have a detector that lets you look at that diffraction pattern. And so at that point, you can calculate the crystallographic orientation of your material. And then you can raster the beam across your microstructure, and at each point get a new diffraction pattern to calculate the orientation. So we're really mapping the crystallography here. And the melt phase doesn't diffract very well, so there's no data there, these black little pockets. So each pixel in this map represents a different diffraction pattern. Okay. All right, so here's some mechanical data from one of these tests. Again, we hit a peak stress that eventually dies off to some approximate steady state. You can perturb the strain rate, and you get a stress exponent that's something like 2 to 2.5. And I piped up a little bit earlier in the week saying this is relatively consistent throughout all the experiments that are done where we have this in olivine, where we have this melt segregation. I personally don't quite know how to explain it, and I think it's indicative of something interesting. We can talk about that more later. Okay. So we can see the segregation of these samples. So this is a map of aluminum concentration, and you see this nice big melt-rich band where there's more aluminum in the melt.
What's the sense of shear in that picture?
You'll see in this next one, it's actually in and out of the page. Yeah. So what this is part of a larger data set, and I'm only showing about 2/3 of it. That's a strip from the outside going all the way to the inside. Right? So the top is moving towards us and the bottom's moving away from us. And this is the outer edge, and here we see strong segregation. As we move in, the segregation is a little less obvious. Also, the melt fraction's higher in the center. That's the base state segregation that we heard about earlier in the week. Here's the crystallography just for this part of the data set, which is that sort of length. And there's interesting things. You can almost see band-like structure in the orientation coloring, right? Okay. So, this is all a digitized data set, so we can try and be quantitative with it. First thing to look at is the melt fraction as a function of radius, which remember is also a proxy for shear strain. And we see the melt fraction is higher in the center and it dies off towards the edge. Okay, so that's our base state segregation. This green curve is showing a prediction for what the stress magnitude is as a function of radius, and it's a complicated nonlinear function, and it's difficult to approximate, so you have to make some assumptions to get that curve, but just to show you that it is complicated. Okay, so here are some of the textures, right? So you have to read this from left to right and then go down to the next row. So small shear strain going across and down over to here, pretty large shear strain, about 10. And there's not a whole lot of difference between any of these. And this is bizarre. Okay, we do see, weak maxima normal to the page in the 100 axes. Okay, these are very consistent with everything that's been seen before. But the orientation of everything, the strength of everything evolves very little. And this is bizarre. Okay. All right, we can try and quantify the bizarreness. Yes?
Was it all from the same sample? I
this is,
From the center to the outer rim?
yes,
Yeah.
yeah, exactly. Yeah, we also have a set where Chow twisted these to different total twists, so effectively different shear strains, and look at a tangential section, which is a little more standard approach. And that is all a data set combined in the next few plots. Okay. I'm sorry, that's not true. These sorts of profiles all come from that one strip along the radius. Okay, but we do have these data sets from tangential sections of a bunch of different samples. Okay, so here are some things, a J index and an M index, and that's telling us the strength of the crystallographic alignment. How well aligned are the grains? And what we see is relatively little evolution. Again, you might pick out a slope, but in the melt-free samples, it goes way up there. The pointer won't go. You go up to values over here of about 0.7, something like that, and it's systematic and levels off, starting at a shear strain of about 5, something like that. So this is very, very different. Okay, I showed this sort of plot of ratios of eigenvalues earlier, and I showed it for the dry case, which is here again as these fainter arrows, just to show you the general trend. And in these samples, the darker arrows show you. So in the dry case, the red arrow goes over there. In the melt-bearing case, the red arrow goes over here. Okay? And the dry case, the blue and green arrows do this. And the dry case, the blue and green arrows go in different directions. Okay? So again, it's very different, even in a lot of the subtleties. Okay, and we can calculate an estimate for the elastic properties, and we see that the azimuthal anisotropy, what you might detect in a seismic data set, is off by about 90 degrees from the shear direction, so that would lead to a way different physical interpretation, and the magnitude of the anisotropy is decreased. All right, so that's the basic data set. And we're going to add to it a little bit after we're motivated by a couple hypotheses for what's going on.
So Lars,
Yeah.
it's just on samples containing 5% melt. You didn't
Correct.
vary the melt content.
Correct. Yep.
So you don't know how it reacts when you have more or less.
I mean, we have these orientation distributions measured for samples that have more or less, not in quite a systematic a way. And I mean, this basic result really doesn't seem to vary at all. In terms of how much there's an evolution, I don't know. Yeah, I don't know. You have anything to add to that?
But the melt content varies across the cylinder. Yeah.
That's a good point. Yeah, that's a good point. So let's see, how much is that?
Yeah, so
Oops.
this is
Yeah. So, right. So this is normalized to 5%. So it's varying by a few percent. Okay.
50%. 1.5.
Right. Sorry. 50%. Thank you.
But look,
Yeah.
it also looks like the bands don't really matter because the fabric's the same from the inside to the outside. So whether it segregates into bands or not,
Yeah, that's
maybe is not.
That's an interesting point. Yeah, that's an interesting point. One thing we haven't done is quantify how segregated this is. I mean, you do see some structure in there. Yeah, that's a good point.
Actually, didn't you say that orientation was very different in the bands than outside the band? And so
Well,
when
that-
you're showing these plots, are you combining the two?
Good point. Good point. It's not exactly what I said, but what the point I was trying to make earlier is that there's a difference between samples that do have bands and samples that don't. And generally, these data sets where we make one plot is coming from a region something like this, and you average all over the bands. And if there's some time at the end, I'll throw up a picture where we can see the difference in a band and outside of the band. And it's subtle, which is why I didn't decide to spend too much time on it. So one thing to point out, though, is that you do see, you see something systematic here with little drops and then quick increases. In this case, it's the texture strength. And the hypothesis is that links to, as you scroll through this sample, regions where there are bands or there aren't. but it's a difficult thing to do because I'm going to make this point a little bit later that the bands are moving around a lot too, right? So where they are at the end doesn't mean they've been there the whole time.
How do you know it's not with strain? How do you know it's with the melt bands rather than?
This fluctuation here?
Yeah.
What I mean, are you suggesting that?
I don't know.
Yeah.
I mean, your
Well, I
strain
think-
is not the same from.
Right, but it is also a linear. I mean, this is the strain is a linear function of radius, but we see these serrations as we move along the radius. If that makes sense. So yeah, you'll see in a second that there are local variations in the way the strain is partitioned. So and they may have something to do with it, and I will. Yeah, that ends up being sort of one of the big points. Okay, I'm going to go on. All right, so make key observations. We get these rough girdles that are horizontal here, but when the melt banding is present, we get these point maxima. Okay? We also have this back rotation of the axes, and there's really very little evolution of the alignment. And the three main hypotheses that have come up in conversation or in publication are one, the easiest thing to do is change the activity of these different slip systems, like what Neil was talking about. So you make it easier to glide on one particular plane in a crystal, you're going to get a different orientation texture. Okay. That can take care of these first two. I don't have a good sense for why it would cause this back rotation, and I would expect there to be a lot of evolution in that case, just like in the dry case, but there's very little. I'll go into each of these in more detail in a second. The second one here is a little bit more complicated to explain, and I'll dedicate a slide or two to it in a second. The idea is that the deformation mechanisms that are occurring can be partitioned. So I should say the deformation is partitioned among different mechanisms in an anisotropic way. Okay? And the way I see it, that can handle these top three, but again, I'm not sure. I suspect my intuition would be that would lead to a more obvious evolution. And then the final place I'll go is thinking about the grain shape and sort of rigid grain rotation, which came up in discussion at the end of the last talk as potentially being important. All right, so let's deal with this first one, thinking about the activities of different slip systems. I should make the point that, these rocks are riddled with dislocations. And here's one of these aggregates. You can see these large melt pockets. The bright spots are chromite, and the olivines, this is gray. And this sample has been purposefully oxidized, and the precipitates in that oxidation process preferentially nucleate on sites of repeatable growth, so on these grain boundaries, and also on the dislocations. So we've decorated all these little dislocations, or these dots and little wiggles. Okay, so tons of dislocations in there. And we've been working with the Department of Materials at Oxford, and there's some guys there who are really good with electron backscatter diffraction, and they've developed this technique that gives you magnificent resolution, so angular resolution on something like a few thousandths of a degree. Okay? And once you have data that precise, you can undergo a calculation that I won't talk about unless necessary, that lets you calculate the dislocations that must be there in your sample in order to generate any curvature. So there's some curvature within these grains. So what I've plotted here are the density of these geometrically necessary dislocations in this sample here. This is on a log scale. So you can see lots of interesting structure in there in terms of the way the dislocations are distributed. But when you do this calculation, what you get out is not just the total dislocation density, you get the density for each type of dislocation that's possible. So here we've said there are 6 different types of dislocations possible, and I made the same map with the densities for each. Now, in the dry case, remember this is a melt-bearing sample, but in the dry, melt-free case, I would expect this to be the highest density up here on the left. Okay? If we need a change of the active slip system to generate this change in the texture, I'll just tell you what I'd expect is this one down here to light up. Remember, this is on a log scale. If I didn't plot it that way, you wouldn't be able to see the nice structure because the high density regions would pop out real strongly. And these numbers are probably too small to see, but this one is a factor of 2 higher density than everything else. Okay, so looking at the defects that are present now, the interpretation then is that we really don't have any evidence for a change in the activity of the different slip systems. Okay, so we rule that option out. Okay.
Lars, is this somewhat proportional to the stress heterogeneities in the system?
It's a good question. It's something we're looking into now, right? Because there's this relationship between the dislocation density and the applied stress, right? And you'd expect there to be a lot of heterogeneity in the stress field in here. And so can you then take this map and use it as a proxy for the stress distribution?
Sorry?
Yeah, go.
Just to follow up, because, so are you talking now about the standard dislocation source model, so Frank-Reed sources, or is that for the Langdon model of dislocation accommodating grain boundary sliding?
So I'm not talking about sources at all at this point. You mean in terms of this measurement here?
Yeah, so that doesn't come into it.
Nope. This is only taking the lattice curvature. So the lattice is curved, and it's sitting there curved right now. It hasn't relaxed. And we say, what do you need to do? How many dislocations do you need to be in there to generate that curvature? Okay. You may sit there and say, well, what about, there could be some elastic strains as well that's causing, some deformation in there, and you see that. And the beauty of this technique is you also get out the elastic strains, okay? And their contribution is very, very small compared to the rotations. That makes sense? Okay. So this is just what's present. There's no interpretation about mechanism. Okay. So this next hypothesis, I'll speed up a little bit just after the slide, but I want to make sure I take the time to give this the treatment it deserves. This next hypothesis, again, what we're doing is saying, this happens a lot as we're treating these sorts of data, is we say that the total strain rate is due to the strain rate from our different deformation mechanisms in an uncoupled way. Okay? They're not talking to each other. They happen independently. Now, as soon as you think of these as being anisotropic, so here, I've put a 4th rank tensor in there, and for dislocation creep, I let it be nonlinear as well, but that's less important. The key thing is both of these are anisotropic, and they may be anisotropic in different ways, right? And that means the resulting strain tensor, different components of that tensor, may be dominated by different deformation mechanisms. Okay? On top of that, as Boris pointed out, that the stress and the strain rate fields are probably really heterogeneous. So this is a full field simulation of an aggregate of olivine that's only deforming by dislocation slip. And there are a lot of caveats to this, but this is the strain rate field, I should point out. It gives you the sense that because you have all these anisotropic grains with anisotropy in different orientations, their interaction is actually really very complicated. And you have quite a bit of heterogeneity in the strain rate field and correspondingly in the stress field. And linking that into the fact that they're anisotropic is only going to aid in your ability to have some components of the strain rate tensor accommodated by different mechanisms. So what Ben suggested was that if we have an anisotropic melt distribution, so we have lower contiguity on this face, then the dominant shearing in this situation will be preferentially accommodated by diffusion creep, which doesn't have a very strong crystallographic control that we're aware of, and so would contribute less to the crystallographic rotations. Okay? Whereas some of the out-of-plane components of the strain rate tensor, right, are going to be dominated here. These red planes are interior to the grains, and that's going to let you have shear in other directions different from the dominant macroscopic shear direction. Okay? And so I think based on this sort of picture, if you believe that rough model, you can explain the girdling. Okay? And the next question is, can you explain the formation of this point maximum? So another technique that's come up recently, so this is in a geology paper last year from Zach Michaels, is a hypothesis that your dominant lattice curvature, your lattice, you can think of it as curved around one axis, and the dominant axis of curvature in all your grains summed throughout your aggregate is going to roughly parallel the macroscopic vorticity. Okay, so here's simple shear, and these axes are roughly pointing out of the page. Okay, now this is a dislocation-related process. So if in this previous example, all the dislocation activity is coming in and out of the plane, then we'd expect a vorticity associated with the dislocation activity that's different from the macroscopic vorticity. Okay? So that's basically what I said here, and here's a measurement of this. Okay? So these axes of curvature are dominantly parallel to the vorticity. So this is exactly what you'd expect if most of the dislocation activity is just doing what you would normally think it's doing. It's following roughly close to the macroscopic kinematics. Okay. So in that case, maybe this sort of mechanism can contribute to this girdling, but it's not strong enough to have large enough strain just from dislocation motion in order to generate these sorts of point maxima. Okay? That's the basic interpretation here. All right. Yep, I'm getting there. So now what about the melt-rich bands? Okay, so the first thing we can do is say, here's no bands, here are bands over here, and we have this back rotation. And what Ben Holtzman suggested is that you have local changes in the dominant shearing orientation. Okay, so the bands are oriented at roughly 20 degrees, and they're weak zones. So you would expect to localize deformation on them, and to get a net deformation that matches the macroscopic deformation in the melt pore regions, you would have this back rotation of the shear planes. So that would suggest that, this is forming largely due to the activity of dislocation glide, and that is on this back rotated shear plane. We don't really have a better explanation for this. Okay. Now, still thinking about those melt bands, one thing we have to worry about is the fact that they're moving around, right? Over a wide range of strains, they roughly, on average, have the same orientation. But if they were a static material line, then as we shear this top to the right, they would rotate, right? So what must be happening is that they start to rotate a little bit, they come into an unfavorable orientation, they close off, and you open up new bands at a more favorable orientation. So these bands are effectively sweeping through the material. Okay? So at any point, I go and look at this olivine here, it may not be sitting in the middle of a melt band, but it may have had locally high melt fractions in a transient way. Okay. So this comes to the last hypothesis then of this grain shape control on the rotations. And so if we have locally high melt fractions, you reduce your strain compatibility restraints. The grains don't have to interact with other grains quite as much. And at some point you can think of them as rigid particles in a flow. And people have done sort of analog experiments on this and seen this sort of phenomena in mushes in magma chambers. And there's a hypothesis that this can happen in diffusion creep. This is an example out of Takiharaga's lab. And the dark phase here is forsterite, the light phase is anorthite. And you have a strong elongation of the forsterite, and this was deformed in vertical extension. And so the thought is that these particles rigidly rotate so that they're aligned with the extension direction. And in this system, the shape of the grains is controlled by the crystallography. So there's a crystallographic control in the shape, which imparts a dominant crystallographic orientation, in this case, A-axis vertical.
The question there is, so the material orientation is the same orientation as the grain shape? Those are two, it's different normally. The material does not have to have the same orientation as the grain shape.
Correct, yeah. Correct, yeah. So you mean the outline of the entire sample? Is that what you're saying?
I don't know, if I draw now a grain here and I don't tell you about the material, you can impossibly know what the material orientation is within the grain.
I guess I'm just not sure what you mean by material orientation.
LPO and SPO the same thing effectively, or are they totally decoupled? I think that's the question.
In this case, they're coupled, okay? Because It has to do with the anisotropy in surface energy, the interfacial energy. In this system where you have forsterite associated with anorthite, particular boundaries are more energetically favorable, so they tend to be longer. So the shape is controlled by the crystallography. And that's the point I'll make right here. So that was forsterite anorthite. In our case, we have olivine and basalt. Now, if we want shape to control this pattern that we see, I'll just tell you what we need is 001 longer than 100 longer than 010. Okay? And so here's a data set from olivines in basaltic melts from Hawaii, and plotted on a diagram that's the relative lengths of 100 versus 010 versus 001. And so this cluster of data is roughly in agreement with this. These guys end up being relatively similar. This one's very short. Okay. All right. So Chow went ahead and made a bunch of these measurements looking at grain shape. And to really understand it in 3 dimensions, you have to do it on a variety of sections. And we want to relate it to the crystallography. So we could take the crystal distribution, pick out just the grains in a certain orientation, and then look at the length of an ellipse fit to them. Okay, so in this case, the 001 axes are longer than the 010 axes. We can tell that from this section. Okay, so we made a bunch of these measurements, and I'll just flip through them quickly because we don't need to worry about the details. Here's a separate section, and we get another set of inequalities. Here's a third section, another set of inequalities. And if you add all those up, what you find out is we get exactly this relationship. C is longer than A, which is longer than B. Okay, so that's all consistent with yeah.
You could make 2 ratios out of that, right? And potentially the rate at which the fabric evolved would be related to those ratios. Is there any validity to that? I mean, if 2 were equal, then the rate at which that fabric would evolve would go to 0. Right? It would stay as a girdle.
Yeah. Yeah. That's, well, yeah. So if you're saying if you have this situation, is that right?
Yeah.
Do you have plates and they're rigidly rotating? You only have control on the short axis wanting to be in the shear plane, but everything else is sort of free to jostle around.
Give you a girdle, right?
Yeah, which will give you a girdle. Yep. But in this case, we see that they are unequal. Right? So they're not exactly like that.
Yeah.
Yeah.
Okay. Yeah.
Okay. So it's like this, but it's slightly elongated. Okay. All right. So we could use this to explain this point maxima. And if this is a situation where we have a melt-rich band that moves through a sample, it frees up your compatibility constraints and allows the grain shape to control the rotations. Okay? But then the band moves away, and you drop the melt fraction, and you go back to the dislocation processes being dominant, and then you go back to the other one, and you're always alternating back and forth. You might expect that you never form a strong texture, and it doesn't evolve very much because you're always stuck oscillating around there. Okay, so here's our crude drawings. This is the last thing I want to show. Okay, so you have some melt alignment without segregation, and if there is some anisotropy in the distribution of different deformation mechanisms, you can suppose that you start to get some girdling, but the dominant dislocation activity is going to put most of your A-axes horizontal. Okay. Once there's segregation, when you're not in a band, your shear orientation tilts. You tilt your dominant orientations. But then when a high melt fraction region sweeps through, okay, because of the anisotropy and interfacial energy, you develop these shape crystallographically controlled elongation of your grains and shape-controlled grain rotations. Okay? And that wants to orient in this sort of direction. And so, the simple thing we want to do is think about these being summed together as you alternate from one process to the other. And conceptually, you get something like what we see. Right? So that's where we are. We're at a conceptual model. And what I'd like to see is the rigorous mathematics be put to this, where we need a way to incorporate, this came up in the discussion after the last talk, a way to incorporate the shape-controlled grain rotations in a transient way, so it's fluxing on and off, in combination with the crystal plasticity. Okay, so,
Lars?
yes?
And when you say locally high melt fractions, could you remind me how?
In the bands, the melt fraction can be something like 15%. Sometimes it's higher, sometimes it's a little lower. Yeah. So I don't think you're above the rheologically critical melt fraction. I don't think you're really disaggregating, okay? But really, it's a relaxation of the compatibility constraints. Okay. I basically said all this right now, but just 2 points looking forward. When we think about how to say what the viscosity is in a part of the Earth that's deforming like this, what do we say? What's the rate-limiting step here? Right? This material has a weird stress exponent. Where does that come from? Okay. And then what I didn't really talk about is the anisotropy and viscosity. Okay, we know crystal plasticity imparts mechanical anisotropy, and Andrea will talk about that. We know that having a layered composite is going to impart some mechanical anisotropy. And we know that at the grain scale, having an anisotropic melt distribution may impart some anisotropy. So which is the most important when you think about the anisotropy of the whole aggregate? So, I don't know, really open questions. Okay, I'll stop there. I've taken enough time. Thank you. So, a couple questions. I don't know, I'll moderate myself, but I'll kick myself off too. So.
I mean, I do have to ask, so you mentioned the dry or nominally melt-free aggregates. Do you know how much melt is in those?
Yeah, I mean, it's hard to find a lot of melt pockets, maybe 1% or less, something like that. Generally less. Every now and then you find one, that sort of thing. I mean, because it's hard to image and find, we haven't been looking for it in a very rigorous way, right? But as we've documented our starting materials, especially the FO50, it's less than 1% for sure. Yeah.
And is that concentrated in any way in bands, or I guess
No.
you haven't?
No.
That's
Yeah,
random.
there's too little to say anything quantitative about. If there are more melt pockets here, I mean there's so few, right? Most of the time you just can't find them. We're not really zooming into each triple junction to start looking for that little bit, right? And that's largely because the textural evolution, I should say the crystallographic texture, the way it evolved is just very consistent with what you'd expect for the lattice dislocations being the dominant control, right? Yeah.
Have you looked at systems where you don't generate bands? Because your mechanism suggests that actually that's fairly crucial because of getting the relaxation of the constraints.
Yeah, so you mean effectively an analog to this, but where there isn't that segregation at that length scale.
Or just put the melt fraction down. I mean, you say that the high melt fractions you get this, but 1% you don't. Well, what about in between? When how much can you put in there and not get it? And does it still happen then?
Right, that's a good question. I mean, so the average melt fraction by volume in these samples is 5%. So we're wondering at 3%, is there a difference? And I don't know.
At 1% you say doesn't form bands, 5% it does. Well,
Yeah.
About
So
3%.
I don't know. David, do you know the data set? How many samples are there with 3% melt fraction?
I don't know. There are actually some with 1% where you do begin to see segregation.
Yeah. Okay. So that would be interesting to look at the
We
crystal.
have fabric data for it.
Right. Exactly. Yeah. No, that's a good suggestion. Yeah. Yeah, Boris. Sorry.
Some of the pictures seem that your melt bands are about, like, let's say 5 to 10 grains wide, if I saw that correct.
Okay.
General band.
Good question. Let's find a picture. In
What earlier on.
not that. Maybe here, like that. It's kind of hard to tell what what grains are in here. Say again. Okay.
Yeah, this one.
This one here. So I don't know, what do you do? Is this whole thing one band, or is this a couple bands? I'm not sure if the size of the bands has a strong effect here. And in the data set we've really built up, and that I mostly talked about, these were all done at basically the same strain rate, basically the same melt fraction, in order to rule out those as variables that are going to cause any differences we see.
Has someone done these experiments with a different grain size, just in general?
Oh yeah, I mean there's a big data set. I'm definitely not the expert to talk about it in terms of the systematics of the band widths and angles and melt fractions, and I'm not sure I can comment in a way that I'm confident in. So I'm pointing at David because maybe he knows what the key control is on the bandwidth.
We always scale it against compaction length, so we use kind of the McKenzie formalism for calculating compaction length and calculated it that way from viscosity, grain size, permeability.
Which wants to jump in on
I
this?
commented on that, but I mean, Ben's 2007 paper, I think, showed that the stress matters, that at high stresses you get narrow bands, and at low stresses you get wide bands. But the question that I had, I mean, kind of following on from what Dan was asking, because I think it would be really helpful to deconvolve the role of melt bands, and that adds an enormous amount of complexity.
Yep.
What if you did experiments at 15-20% melt? Then SPO would definitely be dominant everywhere, and you wouldn't have to worry.
Yeah, this conversation came up. It's you make the whole sample a melt band, right?
Yeah.
And
The only complication I can think of offhand, and it may not be a complication, is it will be so weak we can't measure it. So I mean, if it were 100% melt, we definitely don't have the resolution. We could redesign the load cell to do it, but without that kind of major stuff. But it's a really good idea, I think. We could certainly try.
yeah, to be fair, maybe we don't need mechanical data. I know that's blasphemous to say.
It's the only part that's sacred.
Anybody else? Matt?
Do you see any difference in the microstructure around the role of grain boundary migration in your melt versus melt-free?
In the microstructure, what do you mean? Do you mean?
You see serrated boundaries, lobate boundaries, elongate grains?
No, yeah. I mean, I think we'll see in Andrea's samples, the natural samples, the grain morphology is much more complex. But I think in most of these samples, the grains are reasonably well shaped. Layla, can I call on you and say, in your grain growth experiments, you ever see weird sort of amoeboid looking grains? Yeah. So, I mean, it's one thing to think about in the next talk is about how the differences in activity of grain boundary migration affect things. Okay, maybe I should let everybody have a coffee break. Yeah, and we'll come back in 25 minutes at 4 o'clock for the last presentation from Andrea Tomasi. All right, thanks again.